and it's circulating in the body for a while. And so this is the first paper about the EPL effect, and published in 1986, and from Matsuda and Maeda from Japan. And so they use the albumin this time, and looking at they using the Evans blue and albumin complex, just mixing it, and then injected it into the intravenously, and they find it out that the melanoma tumors and the accumulating melanoma tumor for a while, this is the permeability, and if they are directly injecting in the melanoma and this complex, it will retention, and this is just the Evans blue disappeared within 3 days. So, but after that, they think this is just a passive targeting, and so many people are think about this, and this small size within less than 100 meter size, and going to the maybe a cancer accumulated by EPL effect. When we're looking at the FDA approved drugs, and only 2 is available right now, and Doxil, and from the Shiej we developed this, and Abraxane and Desai, and they developed this. And so many Doxil derivatives now available, but only one drug, some Abraxane, using based on the albumin nanoparticle. Even if it is just around the 150 nanometer size, but it is if it is injected into the human and IV, and it dismantled and disintegrated into the each albumin, and then circulating as an albumin liver. So albumin, why we can use an albumin as a carrier? And albumin is constituted as just around 60% total plasma protein. Is so much abundant. It is already act as a natural carrier. Is at multiple binding sites, and so if you're looking at the thyroxine, propofol, some drugs and some hormones are, if we take injections or natural hormones are carried by this albumin, because albumin has a long circulating half-life. Albumin is produced by the hepatocyte and liver, and it's just around the 20 days like antibodies. And so if some drug is binding to the albumin, and it increases the circulating time, half-life in our blood, and slowly releasing into the other tissues. It is also very soluble. And another thing is the albumin is rescued by the FcRn receptor like antibodies. Not just the size matters. And antibodies in our natural nanoparticle inside our body is circulating for a long time because of the FC. It binds to the FcRn in the liver, hepatocyte, and in the endothelial cell, many macrophages, dendritic cells. So many nanoparticles are engulfed by the Kupffer cell, macrophages, and the endothelial cells and the hepatocytes, but it does not go recirculating again. But if the antibodies, albumin, is bind to the FcRn in that kind of cells, it recirculating into the blood. And so if the antibody is denatured and maybe the albumin is denatured, then it's disappeared, it degraded, not binding to the FcRn. So this is albumin is binding to the FcRn here, but IgG-Fc has a different the binding sites and the FcRn. So this is the pictures that we take in the patients and protein losing enteropathy. And the patient with protein enteropathy and albumin is secreted through the bowel, small bowel. So this is one patient injected technetium albumin, and it is circulating, and you can see looking at the base of the heart. And if you take pictures over here, and you can see clearly heart because it is blood pool imaging and the major vessels. And some of them are still, we can see slightly the marrow and also the liver. But then, as the time goes, in the 24 hours after injection, you can see some albumin is secreted through the small bowels. That's the positive cases for the protein losing enteropathy. But if you sometimes looking at here in the liver is almost the same activities. Actually, this liver is visualized because of blood pool imaging. So we also tested in the technetium albumin in the tumor model, mouse model, generated a couple of 1 prostate cancer cells in here. So if you're looking at imaging of tail vein injections, 30 minutes after 4 hours, 24 hours, it's slowly accumulating into the tumor. But if you're looking at this imaging, much higher uptake in the liver. So during the conjugating technetiums to the albumin, we used in the reducing agent, a large amount of reducing agent. Sometimes it damages and denatured the albumin, so it is not binding to the FcRn, so many hepatocytes and those Kupffer cells involved in it. It's the death, so we have to radiolabeling with mild condition. So I have a chance to work with Professor Sandra Zhang, who is biologist, molecular biologist, developing anti-HER2 aptamers. And when we first met together, and we just tested the aptamer itself and radiolabeling directly, and injected it into the tumor-bearing mice. Actually, this is HER2 aptamers we injected, and we inoculated this as KB cells, breast cancer cells of expressing HER2. And tail vein injections, you can see just the heart and liver and the kidney, but finally it's excreted through the kidney and bladder. The sum is going to the liver after 2 hours, but we don't see any difference between the HER2 negative and HER2 positive cell because it is so small, and so in that case, very rapidly excreted. That's why we need some nanodrug deliveries to make some long circulation. And we try to use the albumin in these cases. And so serum albumin conjugated to aptamer, and on the other side, are conjugated copper 64 for the PET imaging. And so if you're looking at this, just this human serum albumins, you can see the both positive and negative cells. And because of it is just in the EPR effect, I think. We use the specific aptamers and only the HER2 positive cells. This is a biomarker targeted imaging. And so if you're looking at their biodistributions and 1 hour and 22 hours and after, this is just the aptamers and their tumors uptake. It's much less than that one. This is KPL4, this is negative cell, this is a positive cell. It's slightly different, but if you're looking at conjugated albumin and the aptamers, a much higher uptake almost. This is just around 2 or 3%, and this is 10%, is increasing. Just around the 3 times fold or increasing. And so we did, we take it out the tumors and excise tumor ex vivo, and we can do an autoradiography. This is copper 64, just around the 12.7 hours half-life, long half-life compared to the other F18 or the half-life versions. And so we can get imaging, and so we can see the high uptake in here. And also, we conjugated some dual labeling with the fluorescence materials. You can see this is just a HER2 imaging. This is an aptamer and imaging. And so in this case, it's conjugated aptamers as a quietly coincide and co-localizing of the HER2 positive cell. So I had a chance to work with Alex Krause in the Tumor Biology Center in Germany, and who is already studied in the clinical trial using the human serum albumin conjugated on the one side of doxorubicin, the other side is galactose, and the galactose is going to target the siloglycoprotein receptors, which is expressed in the well-differentiated hepatocellular carcinoma, and also non-hepatic cells. So he wanted to test in there a different number of conjugated, how it is a different behavior in vivo. And so he conjugated raclosamine, actually galactose on the surface, the number 8 on one human serum albumin, 26 on one human serum albumin, and 56. There's a number of increased in there. Just in vitro testing, you can see the higher uptake. And we compared with the 3 different cell lines. Hepg2 cell will differentiate, which is overexpression of cytoplasmic receptor, and Hep3B cells in the fully differentiated cellular carcinomas in the so less expressed, and HT29 cells, human colon cancer cell lines, which is not expressed, and a cytoplasmic receptor. And so when we tested it, and the number, different number, and you can see here, and this is just a 5 minutes, and just it shows blood pool in case of the human serum albumin, and 10 hours, 24 hours, 48 hours, 46 hours after, and we get this imaging using the Genesis in this very simple benchtop PET machines. And you can see here, 3 different tumors are well visualized, almost the same, because it is just a human cell albumin, and without targeting variety on the surface. But the lactosamines are increased. You can see disappearing the other 2, only well differentiated, and the cellular carcinomas are visualized. So this means that we conjugate on the surface of the albumin with the targeting varieties, and it going to the target, and not to the target. So it shows a different behavior. So making albumin, making some targeted imaging therapy as well. And this is also radiography data. So we now using click chemistry to make some more not the severe conditions for the denaturing the albumin. So we're using the normal pH and room temperatures for this kind of conjugation chemistry. We're using the edible CP0 on one, and the other is lotite is a chelating agent for the copper 64 and many related metal, and the N3 is reacting with very rapidly and a low pH condition. And so we try to use a different number of N3, maybe control it, how much and conjugated on one albumin, you can manage it. And so we tested on the different number of conjugation. As the different number, the conjugation, the number is increased, we can see there's some more liver imaging. It means it's denaturing. And so just the mild conditions is much better than the harsh conditions. And then we have met this kind of article that just the serum albumin is not just a non-targeted and passive targeting. Some may be affected on the maybe distribution in vivo. One of them is SPARC. SPARC is secretory protein acidic and rich in cysteine, which is many cells excreting an endothelial cell and skeletal muscle, fibroblast, and a range of tumor cells excreting this one. So they reported that the SPARC may be related with some targeting the albumin. So we tested. And we tested many cell lines. Some of the cell lines, such as PC3 and the KB cells and breast cancer cells, are overexpressing O2 is negative for the SPARC. But glioma cells, interestingly, very highly expressed. The U8 is MG, and U series is the cell line, established cell line. But GBM28 and GBM36 is the primary cell line from the Seoul National University Hospital, also well expressed in the SPARC. And so either in the PCL, RNA level, and the protein level. And so we tried to make some of the SPARC knockdown cells using the U887MG cell, because how the SPARC is negative, positive is behaving different. And so when we tested it in the in vitro imaging, this is the SPARC negative cells, not much actively accumulating in albumin. This is just the human serum albumin with conjugated with the Cy5 dye. So it's much different. But if you and externally in the SPOC treatment, it is also almost behavior the same. So SPOC is in the cellular level is a lot more. And we want to do this some in vivo test. And we inoculated one is a U87MG and the knockdown cell on the other. And when we tested it, this is ex vivo fluorescence imaging. It also showing the SPOC knockdown cells is not SPOC is not expressed. And alpha smooth muscle cells, we will show you their endothelial cell, smooth cells, and the vessels. We will look at you. But it is quite interestingly, and that U87MG, the SPOC positive cells in there, it shows some extravasated in the albumin into the tumor cell. But if you're looking at the SPOC knockdown cells, you don't see any uptake in the tumor. Only the blood vessel is visualized, not escaped. We are not sure. That's what we are still doing. And so SPOC may be related with their active targeting of the maybe human serum albumin to tumors, maybe in case of the glioma. And so finally, we want to try to click chemistry using even the therapeutic radioisotopes such as lutetiums and yttriums that we can conjugate it. In that cases, we can treat the cancers using the both chemotherapy and the radiotherapy at the same time using the same nanoparticle. So finally, we will be looking at the molecular imaging because we radio labeling on this albumin or other nanoparticles. So each patient we can get the imaging and they're making some treatment strategy for that specific patients, such as radioiodine therapy. So every treatment we can get imaging that the drug is really going there in that tissues. And this is our teams, and I'm chairman of the Department of Nuclear Medicine. Most of the albumin work is done by the research professor Myung Songs in here, and also recent work is master students in Chung Han-jo, who is also here. Thank you very much.
Thank you very much for explaining us the difference of albumin as a product approach to the in vivo radionuclides. Okay, open for question.
Compared to PET, the albumin itself can help the longer circulation, compared to the without albumin. So, is the albumin help the stealth effect of the drugs, or what happens when it comes to text with the nanoparticle? Can it be acted as oxidation, or what is your opinion of the comparing the comparison of PET and the
Okay, do you mean there albumin conjugated on the maybe a surface of the nanoparticle, is that right? Such as gold or something like that. It may be helped, but I'm not sure that we didn't test it yet. So, in case of the Ebrexons, it looks like a big nanoparticle, but it is disintegrated in the when we need to look. Yeah. Immediately, yes. So it acts as just an albumin. And so if the conjugated into maybe metals, and the FcRn receptor is much more important, I think. So it should be located maybe on outside, so recognized by it. But the size is somewhat bulky, and so we didn't know that we didn't test it yet. But maybe it works or not. You maybe try it. Thank you.
For the Auditorium name. He will talk on defining cancer center to treatment-based practice.
Yeah, I actually need to upload the presentation. Should I do it here? Thanks. Okay. Okay, thanks very much for the invitation. Okay, let me start by showing you this picture, this figure. What you see here in this part over here, this is an overall survival curve. This is actually the one that we have with Abraxane. As you know, Abraxane is one of the main successful nanomedicines that we have now in the clinical practice. We're using it to treat breast cancer patients and also pancreatic cancer patients. This is what happens in the pancreas, in pancreatic patients. What I'm going to show you here is actually this. So the fact that even though we are improving the survival of these patients, still there's a lot of window of improvement. And as you can see here, so at the end, eventually, a very high percentage of these patients still die. So it means that we still have to confront a lot of different issues here. And there are two main questions here that we would like to address, and we have to address urgently. One is how to avoid resistance to current therapy, because this is probably what happens in these cases. So patients die because tumors become resistant to therapy, and because they spread and they cause metastases everywhere in the body. So at the end, the patient dies. So how should we avoid this tumor resistance? How we should avoid this metastatic spread? So there are different mechanisms, and I'm going just to overview some of them very fast. Just that might explain why tumors become resistant. One of the mechanisms is that there's a bunch of molecular mechanisms, a lot of molecular pathways involved in a single tumor cell. This is just an example of some of the pathways which are involved. So it means that eventually, if you knock down a very specific target gene to treat the tumor, to kill the cancer cells, because of new mutations and epigenetic modifications always confer new tumor resistance to current therapies, they modify the molecular background of those tumor cells. Eventually, resistance appears. So, and this is something that we have to take very carefully when we are designing, which is what's happening in the last 15 years, I should say, molecules which are very, very much targeted directed. So it is fine because they're quite powerful in the sense that they show a lot of efficacy, but at the same time, the period of resistance is much higher. In fact, if you check the attrition rates of how these new therapies fall in phase 3 clinical trials, they are almost around 70% of the drugs are failing in that phase. So, whereas more general drugs, the attrition rates that we had in the past were only quite high, but still lower than that in the range of 50%. So. How nanomedicine might help to overcome this? Well, the main issue here is to be able to provide a combined therapy. So, and this is something that it's not easy in the clinical practice because of the long and the high level of toxicity that combination therapy produces. So, in that sense, nanomedicine might be a possible solution. We're not going into that question though. The MDR complexes are also another reason why cancer cells are resistant to therapy. Those are very complex protein complexes on the surface of the membranes of the cancer cells, and what they mainly do is that they pump out the molecules that get inside. So every time that you give a drug, this is what you see here in the part of it here, it gets captured by the mechanism, by the complex, and it's pumped outside the drug. So this is a mechanism that the tumor cell uses very frequently, and in fact many tumor cells just increase very much the level of expression of these complexes on the membranes. It is thought that nanomedicines, in the way that they enter into the cell and they internalize, because they deliver the drugs very much at the very inner part of the cell, they escape eventually and in great percentage of the cases from these mechanisms. So that's another way how nanomedicine might also help to overcome resistance. But let me go to the main focus of this talk, which are the cancer stem cells. Cancer stem cells are also the other main mechanism why tumors are resistant to therapy. These are a very specific type of cells, very small numbers of cells within a tumor that are very rare, highly tumorigenic. They have this cell renewal ability, and they are highly resistant to therapy in normal conditions. They are the only ones to have the ability to survive in non-addition conditions, and this means that these cells are the ones that will spread. They will extravasate from the tumor, will go to the circulation bloodstream, and they will go somewhere else to cause metastasis. So they are the responsible ones for the metastatic spread. Okay. So in general terms, what we are doing when we treat tumors with classic chemotherapy, and imagine that these cancer stem cells are those ones here in red, whereas the tumor cells, which are non-cancer stem cells, are those ones here in this brown color. What we do with classic chemotherapy is to mainly kill and eradicate a lot of tumor cells, but not that much those cancer stem cells. So at the end, what we have are surviving some cancer stem cells that they will get in place, and eventually they will be the reason why a tumor has recurrence. They have the ability to facilitate this tumor growth. So initially, one would think that by targeting cancer stem cells and killing them, and combining this with the classical chemotherapy, it will come to tumor remission. So one of the main issues that you have to confront when dealing with cancer stem cells is that because they are very few in a single tumor, they're very highly seen. I mean, it's very difficult just to work with them because you don't see them. So we have developed this system which is based on this specific vector here. What you see here is a vector, genetic vector that has the expression of a fluorochrome, which is called TD tomato. This stands for this red color here. Under the expression, the regulation of a promoter, which is mainly activated when it's inside a cancer stem cell. So it means that if you put this inside a cell, if this cell is a cancer stem cell, it becomes red. If it's not a cancer stem cell, then you don't see this red color on that cell. So this allows for the first time just to track down these cancer cells and to be able to grow them in any condition, in non-attachment conditions. This is a tumor sphere. We were talking before about tumor sphere, so you can see one of them here. This is this red figure here. And also grow them in attachment conditions if you need to, so we can quantitate them. So what you see here is that cancer stem cells, the level of cancer stem cells in the mammospheres, when you grow them in non-attachment, is very high. It is not on the level of non-red cells. Okay, these cells have all the expression markers that you would expect to find in cancer stem cells, like LDH1. This is a very typical one in cancer stem cells. Those are breast cancer cell lines. Also another ones like CXCR1, for instance, OCT4, CD44, for instance, CXCR1, and also some epithelial mesenchymal transition genes like twist or bimetin. This is an important question here, the EMT. The EMT is a specific pathway that allows cells to become from epithelial cell types to mesenchymal phenotypes. It means that cells that initially are epithelial, so let's say they will not have these cancer stem cell-like properties. By these pathways, they might become cancer stem cells and show these these properties of non-attachment conditions and so on that I was telling you. What happens when you take these T cells and you let them grow? So eventually they grow, they divide, they kind of slow dividing cells, but eventually they rise to other cells which are not cancer stem cells. They, like these ones here that you see here, those ones are not red any longer. Those are tumor cells which are not cancer stem cells, but which came from cancer stem cells. No? So eventually they reproduce the tumor. That's what happens after treatment and after resistance. No? And this is something that you can see in culture very, very often. So it doesn't matter if you take whole cancer stem cells and let them grow, the cells always reproduce the tumor cell line, the mother tumor cell line. So this is done with MCF7, this is from breast. And what you see here is that if you take those cells which are red and you put them on culture, eventually you will have 1% of cells that still are cancer stem cells. So every single tumor cell line has a very specific proportion of cells, a very specific percentage that is kind of particular for everyone, and they always go to that percentage. Yeah? So this is a signal that goes on and on and on. Yeah? So you take, what you see here is the same thing. No? So if you take, imagine that you take the red cells and you put them on growing conditions, so eventually they reproduce, their percentage goes down, 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 until you have these 1% of cells. And these always are stable. So for some reason, tumor cell lines, they always keep this percentage. And it's a different percentage depending on the tumor cell and depending on, for instance, mesenchymal cell lines, they have like 20-25% of cancer stem cells, while epithelial cells, you will find like 1-2%, 3-4 the most. No? So how nanomedicine might help to target these cells and to increase this, the sensitivity of these cells to treatment? One possibility is to use a targeting system. So, for instance, what happens if you treat a tumor cell line with paclitaxel cells? And this is what you see here. What happens with the cancer stem cells? The percentage of cancer stem cells increase. This is a relative percentage. It means that the paclitaxel cell, as well as Abraxane, for instance, it has the capability of killing cells, but it's just that they kill much more tumor cells than cancer stem cells. So the percentage of cancer stem cells increase because of this. Because what this means is that cancer stem cells are more resistant than non-cancer stem cells. Okay. So what happens if we use a system based on of a nanoconjugate like PLGA with PEG and paclitaxel and treat these cells? So more or less it's the same thing like PDX, so they have the same sensitivity. But when we add an active targeting like CD44 antibodies in breast cancer, or for instance in HET116 cell lines, which are from colorectal origin, we use cetuximab, which is an antibody against EGF receptor. Then the figure changes. So it means that if you use a targeting system, the percentage of cancer stem cell surviving is lower, so it means that they are more sensitive. Especially in this case here, for instance, with the CD44. I mean, you use paclitaxel or you use the nanoconjugate with paclitaxel, the percentage of cancer stem cells increase. But you'll see this reduction here when you're using a targeting system. I mean, it's not perfect, but still there are some cancer stem cells that they survive, but you improve this sensitivity a little bit. And this is much, much stronger if you use this cetuximab in colorectal cancer. So probably depending on the tumor cell line and the kind of active targeting that you use, you have more or less efficacy. Okay, so active targeting might be a way to overcome this too. No? But what else can we do for that? So one main issue is to be able to know what's inside the cancer stem cells that might be a right molecular target. No? And this is the case, for instance, of ALOX5. ALOX5 is a gene that is involved in the synthesis of leukotrienes and the arachidonic acid, which you see here. So this gene is overexpressed in breast cancers and ovarian cancer, in colorectal cancer, in lung cancer. So it seems to be a very wide overexpressed gene in many, many different tumor sites. It is not that ALOX5 seems to control the cancer stem cell survival in leukemia cells, and And fortunately for us, there are some drugs like Xylotone, for instance. This is a drug that is an anti-asthmatic drug used on the clinical setting, which is capable of inhibiting ALOS5 expression. The same thing can be done by siRNA techniques, for instance. No? So the idea is, what happens if we just use nanomedicine to target a gene like this? Right? Well, if you check ALOS5 in cancer stem cells and you go into our models, you will see that in black here are cancer stem cells. So the expression of ALOS5 is much higher in cancer stem cells than in non-cancer stem cells. And the same thing in this case here. This is an epithelial breast cancer cell line. This is a mesenchymal breast cancer cell line. So independently of whether we are dealing with a mesenchymal or epithelial cancer cell, the percentage of the increase on these targets in cancer stem cells seems to be the same. So this makes ALOS5 a potential good molecular target for inhibition. And this is something that you can also see here with HCT8 or HCT116 cell lines. Those are from colorectal cancer origin. So it seems to be a general target molecule. Okay. So what happens if we treat these cancer stem cells with Xylotone, for instance? This is this drug that I'm telling you is in the market, no? And it's actually very cheap. No? So what happened? Well, what you see here is that if we use Xylotone on these red cells, on these cancer stem cells from the MCF7 or in the 231 cell line, the percentage of cells, this is an IC50, so what we're seeing here is toxicity, is cytotoxicity. The cell survives much less, so they are sensitive to ALOS5. But the most interesting question to us is that even though Xylotone, which is here in blue, has some efficacy, what is more striking is that this efficacy is much more increased when you use this drug in cells growing in non-attachment conditions. It means that if you take the cells and grow them as mammospheres, in that tumor-sphere in red that I was showing you before, then the effect of Xylotone is much higher. So it means that for some reason probably ALOS5 is more involved in the non-attachment condition part of survival of these cells than when they are in attachment condition. So, and this is good because it might suggest that if you use it in vivo, it might reduce the level of cancer stem cells surviving in the bloodstream, so it might reduce the metastases. No? That's the theory, at least. No? So, what is the effect then of using another strategy like for instance, an siRNA against ALOS5? So here you have the same thing. So the percentage of cells that survive to the inhibition of ALOS5 by siRNA sequences is very low in both cell lines, in breast cancer cell lines. And the most interesting thing is that if you combine the effects of Xylotone and you compare it with how this is combined with paclitaxel, for instance, either using Xylotone or using the siRNA of ALOS5, the efficacy is increased. So this is what happens when you treat these cells with paclitaxel or with Abraxane. As I was showing you before, the percentage of cells surviving of cancer stem cells is higher. Okay, so it means that this is a relative measure of how much resistant are those cells to paclitaxel. If you use Xylotone, this is you see more efficacy in treating the cells. So what happens when we combine these two things? For instance, Abraxane and Xylotone. So fortunately, when you combine this, and we're doing this here with the siRNA sequence of ALOS5, the efficacy is even higher. Okay. Okay, so can nanomedicine help us to provide some new treatment based on Xylotone and show the same effects? Well, the answer is yes, at least in vitro. And this is what you see here. So this is a polymeric micelle that contains amphiphilic polymers and which allow you to load inside the micelles the Xylotone, the drug, because it has an hydrophobic component. What happened when we use free xyloton to treat these cells? As we saw before, they show efficacy. So there's a high percentage of cells that die because of the use of xyloton. What happened when we use these polymeric micelles being loaded with xyloton? So this efficacy increases still much more. This is what you see here. So the delivery of xyloton with polymeric micelles seems to be much better an option than to use xyloton per se. So can we use this also, these polymeric micelles to deliver the siRNA of xyloton, for instance, or ALOX5 as we were talking before? And the answer is yes, we can use them also by just performing some polyplexes with cationic polymers. These can go inside the polymeric micelles, and this is the chemical group that we use. These micelles have a size of around 26, 27 nanometers in size, and this seems to be quite stable, even though they can be loaded with the siRNA sequence. Well, I'm not going into details. They're quite stable in the bloodstream. This is an MTD study. This is what we do when we design a nanomedicine, and we check toxicity in general terms on in vivo. So you give different concentrations to the animals and see if you see some kind of sign that might suggest you some toxicity, like sudden death, for instance, of course, and all this list of features that you have here on the right. In this case, we didn't see any of those, so this is good. It means that seems all this at first sight that they can be used in vivo. And this is how they internalize in cancer stem cells. And this is something that we were very interested with because we need to use something that somehow might be able to get inside the cancer stem cells. So what you see here is how these polymeric micelles behave when they are labeled with fluorochrome, and we we measure the level of fluorescence inside the cancer stem cells. So these micelles, they internalize a little bit better in cancer stem cells than in non-cancer stem cells. It's not that the difference is important, but what is important is that they get inside the cancer stem cells. Okay. So what happened when we assay these polymeric micelles with the siRNA against ALOX5, for instance? So we see this big efficacy compared to the use of non-unloaded polymeric micelles. And this is something that you will see in this cell line. You will see it also in this other cell line. You will see at the level of mRNA expression of ALOX5, but also at the level of other assays like invasion, for instance. If you measure the invasion capabilities of these cells, which is something that is giving you the readout of how these cancer stem cells behave, you have clearly a strong reduction of these invasion capabilities. At the same time, if you go to other assays like transformation assay, this is what is telling you how these cells might survive in non-attachment conditions. So the percentage of cells growing and surviving in non-attachment conditions or in low attachment is very much decreased if you use these and you treat them with these polymeric micelles against ALOX5. And the most interesting thing in that case is that if you combine in these polymeric micelles the siRNA sequences against ALOX5 together with xyloton, then you have a much better reduction on efficacy, on survival. Okay, so this is another strategy. I mean, the first one was just by using anti-targeting. The second one is by knowing a little bit better what's the molecular targets that we can use to specifically target cancer stem cells. This is another example with ALOX5, but still that's not enough. I mean, one of the bad news about these systems is that cancer stem cells are a very dynamic type of cell. So if you get rid of cancer stem cells, what happens in many tumor cell lines, especially in those ones which are from mesenchymal origin, is that they regenerate cancer stem cells. So this is what you see here. So cells, if you take the cells which are not red and you culture them separately, eventually they become red. This is because they activate a kind of a reversion phenotype that bring them from a more epithelial status to a mesenchymal stem cell-like status. No? That's why they become red again. No? What does it mean this is bad news, because it means that contrary to what we were convinced that we were achieving, which was killing cancer stem cells, so this will lead to tumor remission. Now this is not happening, because even if you kill cancer stem cells, there's a reversal phenotype that will give rise again to these cancer stem cells, so the tumor will regrow. So now the question is, if we can target cancer stem cells, can we somehow see and target this reversal phenotype? Is there anything that we can do just to target another kind of internal molecular target that might avoid this from happening? And well, certainly if we want to find something like this, we have to take a look at the EMT pathway. This is the epithelial mesenchymal transition pathway. So it means that epithelial cells can change from this phenotype, which is more polar they have this kind of a specific structure, cell addition, more stationary. This is characterized by a very high level of icadorins, which are these kind of specific protein complexes that are related to the attachment of cells, etc. So they can change from this status to this other more mesenchymal cancer stem cell-like status by changing and activating this pathway. So we thought that probably what we were seeing when we were seeing this reversion phenotype was an activation of this pathway, and this is indeed what it can be suggested when you check on the genes which are overexpressed in these cancer stem cells. You'll see that some of them, like TGF-beta2, like SNAIL2, SNAIL1, for instance, those are genes which are involved in this pathway. So it might suggest that, and they are very much overexpressed in cancer stem cells, so this suggests that the EMT pathway is activated on those cells. So therefore, if you check the pathway, and this is what more or less the pathway look like, there's one gene, there's a lot of genes, but some of the most important ones are this one here, TWIS, for instance, SNAILs, A1, CYP2, for instance, which regulates the level of some other genes, downstream genes, like cadherin or pimentin, N-cadherin, etc., which changes the phenotype of these cells, okay? I'm showing you this because one of the genes which seems to be involved in regulating also this pathway is AKT2. AKT2 is a gene that seems to also regulate the expression of TWIS, and they are kind of involved one to each other. Actually, AKT2 has been related to apoptosis and drug-resistant migration invasion in other models. So we thought that it might be a good target for blocking the CMT from happening. And in fact, if you check different types of cells and you check epithelial versus mesenchymal cells, you will always find the same thing. So you will always find that epithelial cells have high level of icadorine, mesenchymal cells low, sometimes with twist, but the opposite with pimentin. Now this is the typical signature of an EMT. Okay, so the most interesting thing is that if you check in this case the MCF7, this is in epithelial, so epithelial cells have a high level of icadorine. But if you check the cancer stem cells of these cells, they do not behave like the other ones. So you will see that these cells have a low level of icadorine, a low level of twist, and a high level of pimentin. So, and this is a very important message. It means that cancer stem cells, independently of whether they come from an epithelial or mesenchymal tumor cell line, they're more or less the same thing. And this is good news because it means that by treating them, we will not have to make distinctions between different types of cells. So, regarding going back to AKT2, one of the most interesting things is that if you check how this gene behaves during this reversion phenotype, what we saw, at least in this tumor cell line, is that when this transformation was occurring, there was a very high overexpression level of AKT2. It was a kind of a single shot. If you take these cells and you put them on attachment conditions, then what you see is this: a reduction of aldehyde 1, a reduction in NOT4, a reduction in AKT2 again. So it means that while they are in non-attachment is when they have these high levels of aldehyde 1, of OCT4, of these stem cell-like genes and also of this AKT2, and this is related to the reversion phenotype. No? So question is, can we block this reversion phenotype, or can we act against this cancer stem cell by blocking AKT2? So what you see here is what happens if we knock down the gene with an siRNA sequence. If we silence the gene, if we silence AKT2, what we see is that, of course, AKT2 is going down, E-cadherin is going up, twist is going down, and cadherin is going down, another gene like SPARK2. The same thing in these other cell lines. Those are mesenchymal cell lines. They have predominantly an EMT phenotype, so you block and revert a little bit the phenotype, but you don't see big changes in MCF7, even though you can knock down the AKT2. There are no changes, for instance, in cadherin, which is one of the main proteins related to the phenotype. No? So what happens when we perform proliferation assays, for instance, in these cell lines? So the same thing, if we knock down AKT2, we silence the gene, we see a reduction in the number of cells on proliferating, a reduction in proliferation also in this other cell, no differences in the epithelial one. What happened with migration? So the same thing. Cells stop migrating if you silence the AKT2, but only if they are mesenchymal. So if you go to MCF7, which is epithelial, you will not see this. There's no difference. But as I was showing you before, well, the same thing in invasion. You see these differences in invasions. More reduction here, but a strong reduction in this cell line, in this KBR3, for instance. No changes in MCF7. But if you recall, I told you in the very first slide that I show you the pathway that what happened in these epithelial cells are not the same depending whether you see and checking the cancer stem cells or the tumor cells. So what happened if we check the cancer stem cells of the MCF7, for instance? So, and this is what happened. If you check the cancer stem cells on this cell line and you silence AKT2, you see this reduction also in invasion of these cells. And this is something that you don't see if you're checking the non-cancer stem cells. And you have to think that in a tumor cell line, and this tumor cell line, 98% of the cells are this kind, tomato negative. Those are non-cancer stem cells. So that's why you don't see differences when you check and you work with the tumor cell line, with the mother tumor cell line. But if you check the cancer stem cells, you're seeing these differences. And this is important because it means that those are good targets for cancer stem cells, or they're kind of selective targets for cancer stem cells. And this is the same thing if you check how tumor-spheres and mammospheres are produced. So the level of mammospheres is reduced when you're knocking down AKT2 in cancer stem cells, okay, independently of the tumor cell line. And if you check these cancer stem cells, then is when you see the reduction and the silencing of AKT2, then it comes with the increasing of E-cadherin, the reduction of twist, etc. And this is what you will see in the epithelial mesenchymal transition if you knock down this pathway. No? And most interesting, same thing will happen to other cell lines like 231, for instance. This is what you see here. There's a reduction in cancer stem cells, invasion capabilities, there's a reduction in survival, there's a reduction in proliferation, and this is mostly affecting cancer stem cells. No? It seems to be a very right target for that. No? Same thing if you just check on the expression of some of these genes. I'm going faster. So can we use these polymeric mice cells to knock down and silence the AKT2? And the answer is yes. The same thing that we did before with ALX5, of course we can do it with AKT2. And if you do this, you will see that these mice cells, they can, of course, internalize in cancer stem cells, and they can reduce the expression of AKT2, as you see here, change the profiles of the genes and the epithelial mesenchymal transition, either in twist positive cell lines like this, which is epithelial, or negative like this one, which is mesenchymal cell. So at the end, you're changing the pathway, the mTOR pathway, for instance. And certainly you can reduce very much the percentage of cells which capable of invasion. So you reduce the invasion capacity of these cells, and also the cell anchorage independent growth, which is mainly the production of tumor spheres. No? So this is very much reduced by knocking down 882. And now we know why, and this is because it is affecting the epithelial mesenchymal transition in cancer stem cells as a specific molecular target. So, is that enough to stop the reversal phenotype? Well, one question, additional question, is that, well, how else can we, what else can we do to stop this phenotype, this reversal phenotype? One is, of course, knocking down a molecular target. But the other one is how to deal with the main question of why is this reversal phenotype happening in the first place? I mean, if you take out cancer stem cells, how do the other cells, the non-cancer stem cell, know that cancer stem cells are missing? And this is a very interesting question. So, because in normal conditions, cells will not do this reversal phenotype. I mean, they just keep this 1% of cancer stem cells on the tumor cell line. But if you take them out, then there's a lot of cells becoming cancer stem cells. And this is because they somehow notice that cancer stem cells are missing. So it means that somehow it must exist a cellular crosstalk between these cancer and non-cancer stem cells. This might be due to proteins, for instance. And going back to Spark, and we were showing, we were talking a little bit before about Spark before. Let me tell you that Spark is overexpressing cancer stem cells. That's for sure. I mean, this is a secreted protein that you will find in the extracellular media of cultures, especially in cancer stem cells. In PC3, this is a kind of cell which is from prostate. They have a low expression of Spark, but if you check, there are two different types of PC3. There's a very specific subtype of PC3 which is highly metastatic, and another one which is not. The M stands for metastatic, okay? So, interestingly, the one which is not has a very high levels of Spark, whereas the metastatic one doesn't really show high levels of Spark. And this is interesting because Spark is related to cancer stem cell, and somehow this is kind of counterintuitive, because you would think, well, if it's more metastatic, if it's more mesenchymal, then probably we'll have more Spark, and then we'll find it in a metastatic cell line. But this doesn't happen here. But if you take Spark from these non-metastatic cell lines, if you take, for instance, the spheroid growth capability of these two cell lines, it's very high for the metastatic one. This is expected. I mean, it's something that you would expect. I mean, if they're more kind of aggressive or metastatic, they will probably have more cancer stem cells, and therefore the spheroid capability of this cell line will be bigger than with a non-metastatic type, which is this S. But interestingly, if you co-culture this cell line with these ones, or with the media, with the extracellular media, then the capabilities of invasion of the cell line is even greater. I mean, if you take the conditioning media from the non-metastatic cells and you add it here, this goes up. Okay, this is what you see. As it goes up, this SNAIL1, SNAIL2, twist, etc. So genes that are related to cancer stem cell status. So. And this is due to Spark. So if you take Spark and you overexpress Spark in these cells, you increase the invasion capabilities of the cells. Or if you took the conditioning media from the non-metastatic cells, they also influence the metastatic cells to increase their capabilities. And this is a very good example of this. So these cell lines, these metastatic cell lines, have been transformed with a specific vector, which is this one here. This is an SH RNA sequence. It means that it will knock down the gene, okay? But this is a sequence which is regulated by the addition of doxycycline. So this is a conditional expression system, okay? So if you don't add doxycycline, you have the levels, the effect of increasing this invasion with spark. But if you knock down by addition of doxycycline of spark, then you see this reduction, okay? So it means that spark is acting, in fact, as an extracellular protein on cancer stem cells to increase their invasion capabilities, at least in this model. This is also seen in vivo. These are what happens when you inoculate and you overexpress or knock down this gene in vivo. It's the same thing. So if you express the spark protein, you have much more in the cells. If you knock down this expression, then you see a reduction of this tumorigenicity in vivo. So it means that this crosstalk between cancer and non-cancer stem cells might be related to proteins that are kind of circulating from one side to the other one, or might be found in the extracellular medium. But is that enough? Perhaps not. And let me just mention something very briefly about exosomes. So you know that exosomes are now something which is kind of a hot topic in the field. Exosomes are mainly these small small vesicles that are being secreted by cells, so they kind of contain different type of compounds inside. For instance, nucleic acids or proteins or other type of cofactors or molecular receptors on the surface, for instance. But they're known to be able to transmit information from one cell to the other one. And this is something that we knew from many years ago but from the neuronal system. Okay, so question is, might be exosomes somehow involved in this transmission and this crosstalk with cancer and non-cancer stem cells? I mean, we know that spark is doing some effects, but can be the case that exosomes may be also sharing this information and therefore exerting this specific effect on these non-cancer stem cells. Well, this is just to show you that exosomes can, in fact, transport material, transport proteins like GFP, and they can actually internalize in other cells. These are particles that these are in fact exosomes which are being labeled also with fluorochrome, so you can see how they go inside the cells, and they in question of minutes, so they are very fast internalizing this. And what happens if, this is a very short experiment, I'm going to finish with this. What happens if we take exosomes from cancer stem cells and also do the same thing with exosomes from non-cancer stem cells and we play with them, okay? So what happens if we take these exosomes and we use them to see if they can actually transport something that might make more invasive cancer stem cells? It might be the case, it might this happen. So, and the answer is yes, it happens. So if you take exosomes from non-cancer stem cells and you add them in cancer stem cells, and this is what you see here, what you will see is that you have much more level of production of mammospheres, like in this, for instance, and another expression of aldehyde 1 and genes, okay? So they are kind of stimulating the cells to go in non-attachment. And therefore, and this is another experiment that we did similar like that one, they have much more invasion capabilities. If you add exosomes from non-cancer stem cells become much more invasive. So it means that, yeah, we don't know exactly what's inside the exosome yet, but it means that certainly the use of exosomes is a way to communicate and to keep this crosstalk. So what this means is that if we really want to target cancer cells and kill them all, we have not just to target the cancer stem cells by active systems, but we have to know very much which are the main molecular pathways which are inside, but at the same time, we cannot forget about the reversion phenotype and try to knock them either by intervening inside the cells, like specific molecular pathways, but also taking into consideration the molecular background, because there are exosomes, and there's a lot of crosstalk between these two different types of cells, and probably extracellular factors like spark may be one of them. So things will not be easy. Thank you very much. This is part of the team in the Vita Hospital that has been involved in this, like the University of Lisbon. If you have any questions, I'll be more than glad to answer. Thank you.
Showing us the evidence for siRNA-based cancer stem therapy. Are there any questions?